Welcome class. Welcome to our today's topic vectors and scalars. In this video, we will learn about the comprehensive guide to the vector algebra, laws of vector addition and the product and the resolution of vectors. Now coming to the course outline, means what we will be covering in today's class. We will start with an introduction to the physical quantities, then moving on to the scalar and vector definition. Afterwards, we will be discussing about the representation and the types of vectors, and we will covering the addition and subtraction of vectors. We will be doing addition and subtraction of vectors by implementing the laws of vector addition. We will also discuss the resolutions of vectors. We will also discuss the concept of multiplication of vectors, and there will be a special slide for a dot product and a cross product applications. Now moving forward. So basically what is a physical quantity? All the measurable quantities is called a physical quantity. It has many properties. The most important property is also the directional property, which we'll see in the physical quantities. They can be classified into three types: scalar, vector and tensors. Quantity which is described only by the magnitude, means it doesn't require a direction, is called a scalar quantity. Quantity requiring magnitude and a direction is called a vector quantity. Quantity like stress, inertia, which are advanced quantities, are called tensor quantities. They are represented in the form of matrices, and the most important tensor which we have heard and the most common of them is the polarizability tensor. We will learn about them in higher classes. So what is a scalar quantity? A quantity which has magnitude only and no direction is called a scalar quantity. Means here we will not see the direction. Example of a scalar quantity is mass, time, temperature, distance, speed, work, energy, pressure, power, electric current. They obey simple law of algebra. They are represented by a number and a unit. We often speak about his of 15 kilogram. Means his weight is 15 kg, or his weight is 50 kg. In this, we doesn't talk about the direction. So all this quantity where there is no implementation of direction, these all quantities are termed as scalar quantity. Now coming to the vector quantity. Quantity which follow the following criteria are called a vector quantity. They must have a magnitude, they must have a specific direction, they must obey the law of vector addition. So a quantity fulfilling the above criteria is called a vector quantity. Physical quantity having both magnitude and direction are called vectors. So here is an exception. The exception is about the current. Current has direction, but it is scalar quantity because it doesn't follow the law of vector addition. So it is neglecting the third law, which is the third criteria, which is the it should obey the law of vector addition. Examples of vector quantity are displacement, velocity, acceleration, force, momentum, and torque. Now, coming to the comparison of scalar and vector. Now, comparing them on the basis of magnitude. Scalar has magnitude and vector too have a magnitude. Scalar has no direction, but vector has a direction. A scalar follow the algebraic arithmetic addition, but vector follow vector algebra. And now the notation. Scalar has notation in the normal font, whereas the vector has the notation in bold or arrow over it. So how can you represent a vector? Vector can be represented by a line segment which is directed on an arrow. So arrow has a tail. The tail denotes the starting point of the vector. It is also called the origin of the vector. The length, the length of the arrow denotes the magnitude of the vector. It also represents the magnitude of the vector. Now, head. The arrowhead indicates the direction of the vector. Means in which direction the vector is heading. Now, what are equal and negative vectors? Two vectors are said to be equal if they have same magnitude and same direction. For example, if I am taking two vectors such as displacement vector only, I am taking displacement done by me and my friend. We displaced, we both displaced an object for 5 meters in each direction. So here the magnitude and the direction are same. So the displacement vector in the both the cases is equal vector. Now coming to the negative vector. Suppose we are taking a velocity as a reference. Velocity of my friend and velocity of my own self. Suppose my friend is having a velocity of 5 meter per second. I too have the velocity of the 5 meter per second. But I am traveling toward the east and my friend is traveling toward the west. So here the magnitude are same, but the direction of the given vector is opposite. So this is called a negative vector. A vector that is having the same magnitude but in opposite direction is called a negative vector. And it is represented as b vector equals to minus a vector and equal vector are represented as a vector equals to b vector. Now coming to the unit vector. A unit vector is a vector whose magnitude is unity. The sole purpose of the unit vector is to indicate the direction. So, unit vector is indicated as a cap. A cap can be represented as a vector by modulus of a. The modulus of a, also termed as mod a, is called the magnitude of the vector and its magnitude is unity. The key feature of the unit vector is it has no unit and has no dimension. It represents the pure direction of the parent vector. Meant it is showing only the directional properties. So we are now talking about the orthogonal unit vectors. In a Cartesian coordinate system, we have three axes, x-axis, y-axis and z-axis. So unit vector along x-axis is called I cap. Unit vector along y-axis is called z cap. Unit vector along y-axis is called j cap. Unit vector along z-axis is called k cap. Now coming to the zero or null vector. What makes a vector zero? Means zero vector are those vectors which are zero in magnitude, whose magnitude are zero. So, and its direction is arbitrary or undefined. So, any vector such as velocity of a stationary object is a null vector. Significance of zero vector is representing the position of the origin and the velocity of the stationary object or acceleration of the uniform motion. The properties of zero vector are a vector plus zero vector is a vector, lambda where lambda is a scalar quantity, Dot product to a vector quantity with zero vector will always give the zero vector. Zero vector dot a vector is always a zero vector. Now coming to the collinear and coplanar vector. Collinear vector are those vectors which act along the same line or they are parallel lines. They can be parallel means 0 degree or anti-parallel means 180 degree. Now coming to coplanar vector, all the vectors that lie in the same plane are called coplanar vector. Coplanar means the plane should be same. From the name we are getting this. Any two vectors are always coplanar vector. Now defining the position and displacement vector. Position vector. A vector that represents the position of a point related to the origin is called a position vector. And displacement vector is a vector that is representing the change of position of an object in a given time interval. Means if I am taking any position vector and the position vector is changing its position at a given time interval, it is also classified as a displacement vector and it is rotated as a del r vector. So position vector is represented as a b equals to r2 minus r1, where r2 and r1 are respective vectors. I am representing the position vector by the help of a graph. This is point A and this is point B. It is R1 vector. This is R2 vector. This is A. This is B. This is point which I am talking about. So AB, position of AB. So position of AB is R2 minus R1 and these points are related to the origin. This is the origin. Now coming forward. Coming to the vector addition, we have studied about addition in lower classes, but all addition we have studied till now was scalar addition. Vector addition is not simple as scalar addition. The result is called a resultant and depend both on magnitude and angle between the vectors. So what is a resultant vector? A single vector which produces the same effect as produced by all the individual vectors acting together is called a resultant vector. Suppose we take an example of a catapult. I am aiming to a catapult. I am saying that there are two strings. The two strings, when stretched, formed a V-like projection, and in which, in the middle and the center point, we have a stone or anything, and these are the strings of the catapult. This string is pulling in this direction, and this string is pulling in this direction. When released, this center point means the resultant will act straight in the straight direction. Means it is going in a straight line. So the combined effect of this vector and this vector gives this vector, and this vector is called the resultant vector. Now, coming to the triangle law. To add the vector, we have many laws. The starting law is the triangle law. If two vectors are represented by the side of a triangle, means two sides of a triangle, taken in same order, the resultant represented by the third side is always taken in opposite order. Suppose this is the triangle. I am drawing a triangle. Direction is over here, its direction is over here. This is A, this is B vector, this is A vector, and this is resultant R vector. So now triangle law is saying these are representing the two sides of a triangle, this side and this side, and they are taken in same order, but the resultant is taken in the opposite order. Here, same order means A, if you are seeing the vector A, the head of A is lying on the tail of B, but when we are saying the resultant, the tail of resultant is on the tail of A and the head of the resultant is on the head of B. So resultant is on the opposite order, but vectors are in the same order. Thus resultant connects the tail of A to the head of B. It can also be said if two vectors are taken in the same order and are represented as the two sides of a triangle, the third side of the triangle is completed by the resultant and that it is in opposite order. Now coming to the parallelogram law. If two vectors are represented by adjacent side of a parallelogram starting from a common point, the resultant is a diagonal passing through the point. So I am drawing a parallelogram. So these two vectors are represented as the side of a parallelogram. This is the direction over here and this is the direction over here. So the resultant vector will be the diagonal one. It will be always the diagonal one. If I draw it more clearly, you can understand it much better. This side is the resultant and these are the direction of the two vectors. And this is resultant and this is vector A and this is vector B. So these two vectors are represented as the adjacent side of the parallelogram and they are starting from the common point. This is the common point and their resultant is the diagonal passing through that point and the resultant is passing through that point and it is a diagonal. This law is equivalent to the triangle law but provides a better foundation for an analytical derivation of the resultant's magnitude. Parallelogram law is very important to derive the magnitude of the resultant vectors. What was the main analytical result which is required for the parallelogram law? For two vectors A and B acting at an angle theta, the magnitude of the resultant is R equals to root over A square plus B square plus 2AB cos theta, where AB are the magnitudes of the individual vectors. Now coming to the direction of the resultant, if alpha is the angle made by the resultant with the vector A, then the angle of or the direction of the resultant can be given as tan alpha equals to B sin theta divided by A plus B cos theta. This is an important relation. This defines the orientation of the total effect relative to the first vector. Now, coming to the polygon law, if we have more than two vectors, means 3, 4, 5, 6, 7, and we have to add all the vectors, if the number of vectors are represented by the side of the polygon taken in order, then laws stand the same, means the resultant is the closing side and in the opposite order. We have seen that in the triangle law also. Two vectors were taken as the side of triangle in the same order and resultant is the closing side taken in the opposite order. In exactly same over here, the number of vectors are represented as side of open polygon taken in the order. The resultant is the closing side taken in the opposite order. When adding three or more vectors, the principle remains same as the triangle law applied repeatedly. Means here the triangle law is applied repeatedly over here. Now R vector equals to A vector plus B vector plus C vector plus D vector means resultant is the sum of all the vectors. Now coming to the vector subtraction. Subtraction of vector B from A is actually the addition of negative vector B to A. Subtraction can be represented as minus of B. So A plus of minus B is A minus B, which is basically the subtraction of B from A, vector B from A. So magnitude of the difference is magnitude which resultant is represented as S. So S vector equals to means magnitude S is equals to root over A square plus B square minus 2AB cos theta. Coming to the resolution of the vectors means resolution by decomposing vector into two components. Suppose this is a vector and I am decomposing into two components, one through x-axis and one through y-axis. The y-axis is called y sin theta and x is called x cos theta. The process of splitting a single vector into two or more vectors in a specific direction is called a resolution of vectors. This split is called components. Means what I have split elements x cos theta, y sin x cos theta and y sin theta. These are the components. Now it has more implementation. It has implementation in projectile motions and in many other places. So it is an important concept. So what is an orthogonal resolution? Splitting the vector mutually along the mutually perpendicular axes x, y, and z is called the orthogonal resolution, and it is most commonly used resolution in physics. In 2D components, for a vector in xy plane making an angle theta with x-axis, the horizontal component ax is a cos theta, and vertical component ay is a sin theta. So total vector A can be represented as ax I cap plus ay j cap. From the resolution of vector, we can also reconstruct the vectors from the component vertical vector can be recovered. So magnitude of the vertical vector is A equals to root over ax square plus ay square, and the angle of them is tan theta equals to ay by ax, where theta can be derived by using the inverse relation tan inverse equals to ay by ax. Vector in 3D space is resolved along x-axis, y-axis and z-axis and are represented as a vector equals to axi cap plus ayj cap plus azk cap. And magnitude in 3D are represented as a vector a equals to root over ax square plus ay square plus az square. So now coming about the direction cosines, the angle alpha, beta and gamma are the vectors, are the angles that the vectors make with x, y and z axis respectively. So cos alpha equals to ax by a, cos beta equals to ay by a, cos gamma equals to az by a, cos alpha equals to ax by a, cos beta equals to ay by a, cos gamma equal to az by a. And if we add up the squares of each and every cos, it will be coming as cos square alpha equals to cos square beta plus equals to cos square gamma. Means cos square alpha plus cos square beta plus cos square gamma is always 1. And it is a mathematical relation and it can be proved in mathematics. So now scaling of the vector, multiplying the vector by a scalar. If n is positive, the magnitude changes but the direction remains the same. But if n is negative, the magnitude of 2 changes as the direction. So here direction and magnitude changes and direction is exactly the reverse. And resulting quantity has the magnitude of n dot mod a. So B vector can be represented as n a vector, where n is an scalar quantity. Now coming to the section 4, which is the scalar dot product. Means multiplying vector to produce a scalar quantity. Scalar dot product of two vectors is defined as the product of the magnitude and the cosine of angle between them. If a vector dot b vector is written, it can be represented as ab cos theta, and ab cos theta is a scalar value. It is not a vector value. Dot product is always commutative because scalars multiplication is always commutative. So a dot b, a vector dot b vector equals to b vector dot a vector. Dot product for a perpendicular vectors is always 0 because cos 90 is 0. And for parallel vector is 1 because cos 0 is maximum, means 1. So from here we are saying that I dot I is 1, j dot j is 1, k dot k is 1, means I cap dot I cap is 1, j cap dot j cap is 1, k cap dot k cap is 1. Means self products are always 1 and the mutual products means I cap dot j cap is 0, j cap dot k cap is 0, k cap dot I cap is 0. Means rather than the self product, all the products are 0 over here in the dot product. So in the term of rectangular components, a dot b vector can be represented as a dot b vector equals to ax bx plus ay by plus az bz. And these are helpful in finding the angle between the two vectors. In class 12 mathematics, you will be applying the dot product to find the angle between the two vectors. Now, vector cross product means multiplying vectors to produce a vector quantity only. Vector product of two vectors is a vector whose magnitude is the product of the magnitude and the sine of angle between them. Means a vector cross b vector equals to ab sine theta into n cap. N cap represents a direction which is perpendicular to plane containing a and b. Means a cross b vector, the resultant value will be in the direction perpendicular to the plane which is containing a vector and b vector. And it can be denoted by the rule called the direction rule, also known as right hand thumb rule. In this rule, if we curl all the fingers and of the right hand from A to B to a smaller angle and stretch thumb point the direction of the cross product, means the resulting vector is always orthogonal to the both the vectors. Remember this rule is important. So what is the geometric significance of the cross product? So cross product magnitude of cross product equals the area of the parallelogram formed by A and B. So magnitude of cross product is the area of the parallelogram, and half the magnitude of the cross product is the area of the triangle. Now coming to the anti-commutative properties of the cross product. Means as we have seen, the dot product is commutative but the cross product is anti-commutative. Means a vector cross b vector is minus of b vector cross a vector. If they are parallel vectors, means sine theta is 0, so product of the parallel vectors are 0, means self cross is always 0. For the cross bit another vector, there is a cyclic order rule. Means cyclic clockwise. I cap cross j cap is k cap. J cap cross k cap equals to I cap. K cap cross I cap equals to j cap. Here all are positive. If the order are taken in reverse direction, then means in anti-clockwise direction, then k cap will be coming as negative, I cap will be coming as negative, and j cap will be coming as negative. Here I and j are the two planes and they are taken in clockwise direction. So we are seeing that the resultant is always the perpendicular to both the axes. So it will automatically be the third axis. In each case, it is always the third axis. And minus sign is only coming if the order are taken in reverse direction. Means if they are taken in anti-clockwise direction, the minus sign is occurring over here. They can be solved also in the determinant algorithm. Calculating the cross product using the components A cross B vector can be represented as in the form of determinant I cap, J cap, K cap, and below that AX, AY, AZ, BX, BY, BZ in the form of determinant, and by solving the determinant A cross B vector can be obtained. The law of solvent determinant is when we are taking I, we will be multiplying this by this and this by this and adding the both. While taking j, say the second, so we will have to take minus j and we have to multiply a x to bz and bx to az and add both of them. Now coming to k, we have to add plus k also. So k, when we are taking k, we will be taking ax by plus bx ay. After adding all the three I, j and k, we will be getting the determinant, which is the cross product. If I solve it over here, I cap can be represented as, this multiplication can be represented as a y, not x, a y bz, a y bz minus by az minus j cap, again in bracket ax bz ax bz minus bx az, bx az. And now plus k cap. When we are taking k cap, we will eliminating this row, whole row, and this whole column. The same procedure which we are following in I cap and j cap. When we are taking I cap, we are eliminating the whole row and whole column in which I cap was present. And we are cross multiplicating the remaining here and here. Same in j cap, we are eliminating the whole row and whole column and cross multiplicating the remaining. And in k cap, we are eliminating the whole row and whole column and cross multiplicating the remaining. A x This is the way. For K, I am writing the press one only. For K only, I am writing. I have written I and J. You have noticed it over there. I am writing for the K only. AX BY minus BX AY. Now, remember one thing. I will be positive, J will be negative, and K will be positive. It is the laws of the determinant. And determinant you will study in class 12. So, now if you have any question, you can comment me and ask your question. Be feel free to ask your doubts. Next class we will be covering some numericals based on these concepts. Please do like, share and subscribe my channel and comment any suggestions. Thank you.